Hey everyone, welcome back to my channel. Today we're going to be working on problem number 107. It's called binary tree level order traversal 2. There was a prior iteration of a problem, but we're going to be working on this problem. So as you guys can see, I have never worked on this problem before. And the reason I work on problems for the first time in this channel is because I like to keep them more as challenges and to keep them as close to the actual interview process as possible. So the problem states, given the root of a binary tree, return the bottom-up level order traversal of its nodes values. An example from left to right, level by level, from leaf to root node. So level order traversal is basically one of the only BFS traversals on binary trees, in which you traverse level by level. So you have level 1, which is 3, and then level 2, 9 and 20, and then 15, 7. But in here, we're looking for the output to be backwards from bottom to down, sorry, from bottom to up. And that's 15, 7, 29, 20, and then 3. This one example, these two examples are just with values 1 and null. So let's take a look at the constraints. The number of nodes in the tree is in the range 0 to 2000. So there's, okay. So that's a number of nodes, and the possible values are from negative 1000 to positive 1000. But essentially, the values don't really matter, whether it's negative or positive. They could just be arbitrary. And it's already giving us any null pointers, or if the tree node is empty or null, we just return null. So the example is pretty straightforward. There aren't too many edge cases, so let's go over the steps in here. So the first step is to basically, the problem is just do a BFS, right? And the BFS level order traversal is just going to be using a queue. After that, now in the queue fashion, typically what you do is you iterate through every level, and then you add it to the queue, and then you iterate through the queue, and then you add the levels left and right. Now, what we can do if we want it backwards is we can just add the elements to a stack. So whenever we get complete one level of iteration, we add the list elements to a stack, and then in the end, once we've traversed through the tree, we iterate through the stack. But because the stack is going to be in LIFO, last in first out, we will have the order backwards, and because the popped elements are going to be in backwards order. So the runtime of this is going to be O of n, because we have a BFS traversal that's only going to iterate through the elements 1. And then when we are iterating through the stack again, that's going to be O of m, because m is going to be the size of the stack. So it's really O of n plus m, which is technically O of n runtime, and then the space time, and then the space time is going to be also O of n, because we have a list of lists, and then a stack. So that's also going to be O of n. So this is as efficient as I can think of it, and because it's on a binary search tree, that does not make it any simpler. Okay, so let's finalize. Let's add the elements to a list. And then what we need is a stack of list of integer stack of list with new stack, and then we just perform BFS by adding to a queue. So queue integer q equals new linked list. So q is the actual implementation of the linked list. And then if, and let's see, okay, so let's just also add the list of integer final list equals new array list. And let's copy this. Okay, so if root equals null, we return final list, because right now the state of final list is it's empty. Let me just format this. Yeah, sorry. Now what we do is q offer root, and while q dot is empty, so now this is really where our BFS is going to be. Tree node cur equals q dot pull. And before we even do that, we need the size, and size equals q dot size. So then we do for int I equals 0, I is less than size, I plus plus. And here, so tree node cur equals q dot pull if cur dot left does not equal null, q dot offer cur dot left. Also I added integer, this should be tree node. And then if cur equal null, q dot offer cur dot right. Okay, so we need to add okay, so cur tree node cur equals q dot pull. So now this is it. Cur dot left does not, and it's this current size is 1. In this, what we are going to do is list dot add cur dot val, and then once it's done with the for loop, we're gonna make the list here, and then we're gonna do stack dot okay, stack of list dot push list. And Okay, so now that we've added this list in here, okay. So then let's just test it if I am forgetting something for the BFS. List q.offer root while q is not empty and size equals q.size v not cur. Okay, so now cur is q.poll list.add cur.val and then we add in here. Then we come here and size equals q.size and that's 2 tree node cur equals q.poll and which is this one. And so cur becomes this and list.add cur.val. If cur.left does not know, and then no, then you come here, but I believe because then what you're going to be doing is list.add cur.left. So we need to put this q.poll in here in this for loop because it would just add this same one again if we did not. So tree node cur equals q.poll and then again cur, we go to the second one, q.poll, and then if cur.left. Okay, so we are done with the for loop. Once we are done with the for loop, that means we are done with the current level. Then we just add to the stack of list new list, and then we initialize the list to be new array list. Okay, cool. Now we've added the level. All we need to do is while stack dot is sorry, I keep forgetting the name. Dot is empty. Then we just need to do final list dot add stack of list dot top. And then we just return the final list, and let's see if this runs. Okay. Let me run all the sample test cases. Okay, good. Let's try to submit this. Okay, great. This works. Thanks again for watching, and let me know if you guys think there was a better way to solve this problem. Bye.